So previous lectures have been focused on gas phases, gas laws, kinetic molecular theory, etc. Now we're going to move to what we call condensed phases. And here I want to mean liquid and solid particularly, and we're going to find different kinds of solids. There are more exotic forms of matter than that, states. We're gonna stay with these relatively simple solid, liquid, and gas for now. And of course, we mentioned the plasma a bit. So let's start out with a bit of a thought experiment. So here I have a typical table, right? And I want you to imagine on this table a large block of ice, simple H2O, water, ice. So notice that I've drawn this block of ice sitting out over the edge of the table. So there's an overhang here. Now, we can zoom in and let's take a look at what's going on right there at this little corner of this big chunk of ice, the corner that is hanging out over the edge. I'm going to zoom in on it, and I'm going to talk about this lattice structure. Okay, and a lattice structure is one of the ways we start to talk about solids, but we'll get into that in a bit. But here's our lattice, our ice crystal lattice. Okay, now we know that there is a gravitational force pulling. So this right here, this red is an oxygen. These whites are hydrogens attached. So that red-white set there is a water molecule. There's another water molecule. Each of these is water molecules attached in this lattice. Now, we know that gravity should be pulling downward towards the center of the Earth on this water molecule, right? Yeah, so if gravity is pulling this down, now these that are sitting on the table, we can talk about a normal force that the table is applying to hold those, keep them from falling through the table. That's fine. But these that are hanging out over the edge, what keeps those individual water molecules from falling downwards? They are experiencing a gravitational force, so why don't they fall? Now we can extend our analogy a little bit. Here's our block of ice. And now the block of ice is starting to melt, right? And melting is a phase transition. There, we're going to zoom in again. And look at the shape of, you've seen it before, I'm sure, the shape of this drop of water as it just lets go. What happens? It turns into this sphere. Really? Have you ever asked yourself, well, why would it do that? What is holding this sphere together? Why doesn't it just like fly off into all directions like gas molecules of H2O would do? There must be some sort of force. In the previous example, there must be some sort of force counteracting gravity. And here, there must be some sort of force counteracting what's going on with kinetic energy and momentum. When the bits of water are slamming into each other, they're not flying off in all directions. Not really, not very much. Why is that for a solid in the first case, or for a liquid in this case here? So let's start with a quick review of, let's call it a high school version of state definitions. So of the typical three, solid, liquid, and gas. So my usual thought experiment is if you take a 1 decimeter, that's a tenth of a meter, cube on each side of, let's say it's like a glass beaker, except it's made into a cube. So it's 1 decimeter on a side, and that is by definition 1 liter. So we have a cubic shape, and we have 1 liter of volume. Okay, so if that, let's say that is solid in there, maybe something like our water ice earlier. If you dump that out of the beaker, right, it stays a cube, it maintains its shape, and it stays 1 liter. Now let's start over again, and let's say instead of solid H2O in there, we have liquid H2O. So it's just liquid H2O filled up, so it's exactly a liter, and it's in a cube shape in the beaker, right? If I dump that out, it's still a liter of water. It does maintain its volume. However, it'll no longer be a cube. It does not maintain its shape. Then if you let's go full all the way and just close the top of it and say we have that cubic shaped 1 liter of gas molecules, and we open the container, well, that gas actually expands to fill the new container, which might be the room that it's sitting in. So it does not maintain shape, the cube, nor does it maintain volume. It actually expands in volume, just like all the gas laws that we just did. And of course we have, so there are lots of different states of matter out there that you could define. Typically, we just talk about solids, liquids, and gases. You could go even higher energy and strip the electrons off of the outer shells or the outer bands of electrons off of gas molecules, and that's what we call a plasma, when the gas has so much energy, usually thermal that we're thinking about, but it could be other forms, and it has so much energy that it becomes an electrically conductive gas. So now once they're stripped off like that and the electrons become free to move around, that's what we know as that electrical current. It's a little bit misleading to say that lightning isn't plasma. Technically, the lightning creates the plasma moving through the gas, heating it up so much. And actually, when we get it running again, we have upstairs in the chemistry building, we have the ICP, inductively coupled plasma analyzer, and we actually use a plasma in that to analyze elements in a random sample that we might take from the environment. Now, a gas, we're going to say it has no definite volume, no definite shape, so it readily expands or contracts, or it can be compressed. We're also going to say that it is a version of a fluid, and that's because it readily flows when you have a difference in pressure from one place to another. A gas will flow according to that pressure. It can be pressurized and made to move that way. So liquids are also fluids, so they can be induced to move by applying a differential pressure. And you may not have thought about it particularly this way, but anytime you turn on a pump that pumps liquid, say pumping water or pumping fuel to your engine from your fuel tank, you're pumping a liquid, you're inducing a pressure and causing it to move from a high pressure to a lower pressure environment. So we call both liquids and gases fluids, and if it comes up, plasma is also a fluid. Solids don't do that, at least very well. They resist such movement. Okay, now solids, and notice that this is solids 1. There's going to be another one in a minute. So solids, we're going to get a little deeper than maybe we've done before in like your high school classes and stuff like that. So the simple definition of the solid is that it does indeed have a definite shape and a definite volume. If you take that, let's say we had that cube that I was talking about earlier. Let's say it's a cube of iron, right? So if you dump that cube of iron out, it's still a cube and it's still the same volume that it was to start with. It resists that change in shape and volume. But it gets more complicated than that, because I could take a hammer and I could hammer that iron, even though it's a solid, I could hammer that iron into a new shape. I can actually force it to change shape. It resists a change, but not perfectly so. You may have heard of this talked about in the context of, is glass a liquid or not? There is a link here, and it'll be in the PowerPoint that I upload to the course also. This is not mine at all, but it's a really cool discussion of whether or not glass is a liquid. Their claim here in this video is that it is indeed not a liquid. It is a solid. It's what's called an amorphous solid. So we're going to get to that in a moment. So a term that we tend to kind of use less precisely than we might is the term phase of matter. So I think a lot of folks, scientists included, would often interchange phase with state of matter. It's not exactly how we want to do that. So a state of matter are these big chunks like solid or a liquid or a gas or a plasma. But phases of matter are more complicated than that. So here is an old definition from one of my mineralogy textbooks: a homogeneous substance with a well-defined set of physical and chemical properties. I think another definition that might be a little more accessible, but now I can't guarantee you this is going to work perfectly, but it's a pretty good working definition. What I like to say is that it is a distinct bit of matter that is physically separable from other forms of the material. So we'll talk about that in terms of some different states of matter that we could sort of separate into different phases. We could separate, for instance, a solid and an amorphous phase of silicon. We'll talk about that in a bit. So, in fact, we can look at this quantitatively, and we can actually see transitions from using a device we have upstairs in the analytical section called the differential scanning calorimeter. We can look at changes in phases within, let's say a solid. We might use the machine for something like plastics. So what you can do is you can take a plastic and you can increase the thermal energy in the system or decrease the thermal energy depending on how you run it to see where these changes happen. And these represent rearrangements of the molecules within the system, and there can be an energy outflow, exothermic, which is down in this graph. So this is an exothermic change. This is an endothermic change here, where it actually absorbs energy from the surroundings in order to rearrange. This is becoming more crystalline here. And so you might have seen plastics that when they are when certain things happen to them, we can call them thermosets or whatever, you can rearrange them such that under a certain thermal stress they become brittle. And often that is because they're crystallizing from an amorphous version into a more crystalline version, which is actually harder than the amorphous often, but it can also be more brittle than. So these can be different phases, even though both are solid states. They are different kinds of solid, and they can actually be separated from each other physically. Another example I like to use to try to point this out is we think of water ice. So we're just talking about H2O. We're not talking about any other chemical. So all H2O here on this slide. H2O, so when it freezes to become water ice, that's actually not that simple. There are multiple different kinds of H2O solids. And I'm going to show you a diagram in a second, but only the most common form that you're most used to is called 1H. The H is for hexagonal. That's the only kind that floats in water, in liquid water. The rest of them will actually sink because they are more dense, because their crystal structure is such. This is what's called a phase diagram. Now we're going to spend a lot of time on phase diagrams in the next lecture, but this is what one's going to look like. And this shows the phase diagram for water. Now, so at very high temperature and very low pressure, you get gas phase water. Gas phase H2O, I should say, probably. But it is water. And then you get this greenish version here, which is a kind of an in-between state. It is a liquid version of H2O. And then you get, right here is the solid, but it's this, that's that 1H that I was talking about. It's a certain version of H2O ice. It's hexagonal, open lattice. It's a little less dense than the liquid version, which is a weirdness that water does. But you could put that under much lower temperatures. You can actually collapse that structure into what we call ice 9, and that's a much more dense version. Or you could increase your pressure and cause it to revert to ice 2 or ice 6 or whatever these other ones are that change the properties entirely because they're in a different pressure and temperature environment. So what we're going to do here is we're going to look at how you read one of these things, right? So remember that 1 atmosphere of pressure is about 100 kPa. So here's 1 kPa, and that's 1 million PA. So 100 kPa is going to be right about here. And then let's see. Now this temperature scale is in Kelvin because we like to work in kelvins, right? So we're at, around 298K, right? 300-ish. So if we take a look at 1 atmosphere of pressure, 100 kPa, about right there, 25C, so about 298 right there, and we cross-reference those two positions, right? Then at the temperature and pressure that you are currently sitting at, what phase would you expect H2O to be? Well, it ends up in this piece of the diagram. So you would expect water, H2O, sitting in front of you to be in mostly the liquid phase. And you would be right. Hopefully you are not sitting anywhere that most of the H2O in front of you is in the gas phase. That's not real healthy, y'all. I guess it's less unhealthy to be sitting where at a lower temperature where most of the H2O around you is in a solid phase. But I don't know why people live up north. Apparently they do by choice. And I don't know if anyone will have heard of this example before, but how many of you know that diamond and graphite, like would be in a pencil lead, those have exactly the same chemical formula. They're all carbon. Both the diamond and that graphite are made entirely of carbon. The difference is the phase diagram. The difference is that at surface temperature and pressure, graphite is the stable form. But deep in the earth, where you have a much higher temperature and or especially a much higher pressure, then instead of this graphite structure being the stable form, you get this cubic diamond structure being more stable. And so you get a much different phase diamond than you do at the surface where you get graphite. Okay, so now let's move on to talking about a term here, or a set of terms, intermolecular forces. And we're going to talk about remember those forces that I was talking about in the thought experiment to start off the lecture. We're talking about, well, what are those forces involved that are counteracting gravity there? Or what's going on with that? Well, so we need to define some terms, and we're going to talk about, in red I have intra, make sure you hear what I'm saying through my accent, right? Intramolecular forces versus in blue here we have intermolecular forces. Okay, so those are two different things here. So intra means within. So intramolecular means inside a given molecule. Intermolecular forces. Intermolecular means between separate molecules. Okay? So intra, the one in red, intramolecular forces hold an individual molecule together. Intermolecular forces are going to hold one molecule in place near another molecule. And we're going to talk about what kinds of forces help to make those up and how they give things their properties. Now, for the most part, we are going to talk about blue one here, intermolecular forces as being due to electrostatics. So something's positively charged and something is negatively charged. And those charge differences are what's kind of holding on to each other a bit. They are nowhere near as strong as covalent forces, which you would find up here in the red, intramolecular forces. So let's say we have some solid here. We have any kind of solid crystal here, and so there are intermolecular forces, IMFs here, holding this lattice together. But if we start to heat this up, so this is a block of ice in here, right? And we start to heat this up, right? Then we already talked about in previous lectures that heat being added to a system causes the particles to vibrate faster and faster, right? You're giving them more kinetic energy. Average kinetic energy of the individual particles is what we measure as temperature. Well, if we cause them to have more energy, they can get to a point where they can overcome some of the intermolecular forces that are holding them together. And we call that process melting or liquefaction. They can gain enough thermal energy to melt and overcome the intermolecular forces holding them in a rigid solid. Or if you continue to add even more thermal energy, you can get them to such an extent they have so much kinetic energy that the intermolecular forces can't even keep them relatively close to each other and sliding around like they do in a liquid. And that is the process of boiling or becoming a gas. All right, and I'm going to talk now about the strength of different IMFs and what types of bonds. Now, remember that these video lectures do not replace your textbook. You definitely need to read about these different types of forces so that you solidify this idea in your head, okay? Now we're going to talk about three main types. There are others, but they're for chemistry beyond Gen Chem usually. But we're going to talk about, your book calls this one dispersion forces. You might also call it London forces. So dispersion forces, and then we're going to talk about dipole-dipole attractions, and we're going to talk about hydrogen bonding. Now, you might want to review molecular polarity, and remember that you have available all of my old Gen Chem 1, 1211 PowerPoints if you need to go back and review molecular geometry and polarity, because that's about to become important here. We're about to talk about what dipoles are and how they interact with each other. So in order to do that, you need to remember how that works. What's a dipole? What is a polar molecule and what it's not. So you need that before you continue. So if you don't have, pause now, go back, review that, and then come back and pick the video up again. And as before, we were talking about covalent bonds. So this bond, even though it's a polar covalent bond, it is still a covalent bond. So we're going to talk about H and Cl as having a very, in this case, is an extremely polar version of, but okay. It's still, we can call it a very polar covalent system here, holding the H and the Cl together. But that makes for a very polar molecule. So you have a positive end of this molecule and you have a negative end of this molecule. And then, so this positive end is interacting with the negative end of the other, having an inter. So intra, that was the one I had red, and inter is the blue one between these two different molecules. So this is an HCl, this is a separate HCl, and the in between weaker force is the intermolecular force. So I hope that you went and reviewed the polarity sections, because you do need to know the differences in these guys or anything like this. So carbon and hydrogen have a similar enough electronegativity that we say, well, this is the carbon-hydrogen bond is just a nonpolar covalent bond to start with. So this is a nonpolar molecule, and all of the bonds are also considered nonpolar. As compared to, here we have carbon tetrachloride. So consider this, the green one to be a chlorine and the black to be a carbon. Now, in this case, the electronegativity is different enough that this is a very polar covalent bond. This one's polar. This one's polar with the negative end out here towards the chlorine in each case. This one's polar, and that one back there is polar. And here's like an electrostatic map of that molecule. And the negative ends here are shown in blue, and the more positive ends are the red colors. And so, which direction of this molecule is more negative? Well, none. None are, because the negativity this direction, back this direction, they all balance out. So while these individual bonds are quite polar, this molecule is actually non-polar. Then, finally, this guy, which we'll just say is, oh, here we have chloromethane. So C, 3 H's, and then 1 Cl out here. Now, this carbon Cl bond is very polar, and so we have a lot of negativity out this way. And then I guess we reverse the colors here so that red is negative in this case. That's unfortunate. But anyway, this end is more positive, and so you get this polar bond creating an overall polar molecule. And hopefully you will remember having done the vector, dipole vector there. So we have a negative end of that molecule. All right, so warning on this slide for my chemistry majors. The way I'm about to talk about this is a little misleading. It's actually not going to be about time. It should actually be about probability, and we can talk about that and talk about the probability effect of an induced dipole. But a simpler model is if we talk about an instantaneous dipole. So consider back it up and let me say consider a non-polar molecule. Now it's got this slushy pack of electrons around the whole molecule, right? But they're moving around all the time, so you could theoretically have something approach from one side and there be an instant where all the electrons happen to be on one side instead of the other, and so you get a temporary polar setup. Even though the molecule is non-polar, you could have an arrangement of electrons that is asymmetrical and have what's called an instantaneous dipole. You can also cause it to happen by another polar thing being nearby and pushing or pulling on those electrons and inducing a dipole. And so these are very temporary situations, and they're not very strong at all. So these are our dispersion forces, or sometimes called London forces, and they're the weakest of the three that we're going to talk about. And again, I want to stress that calling them temporary is a little misleading. It's really about probabilistics, but that's okay. So if you think about this sloshing around like water in a tank, you could slosh it, even though the tank should just be filled to a certain level. If the tank is sloshing around, then you'll get full on one side, full on the other side, full on one side, full on the other side. Well, as it's doing that, and as this other one is doing it too, then it feels these temporary attractive forces while the water is sloshed up on this side, and then from here it's sloshed away out towards the other side. That looks almost like a dipole for a little while in between. But if we talk about molecules with a permanent dipole moment, which means to say polar molecules. So if we talk about two polar molecules, well, they don't need to slosh back and forth to create a slightly positive and a slightly negative end. They have it all the time, right? And so because they have it all the time, it doesn't come and go so much. This makes a much, much stronger intermolecular force between polar molecules. So a dipole attracting another dipole, that's a much stronger situation than simple dispersion forces. So if both things are polar, then they start to have stronger forces holding them together. They start to like to be a liquid more, or like to be a solid more. And so they tend to have higher melting points than things that don't have a permanent dipole moment, or higher boiling points than things that don't have a permanent dipole moment or molecular polarity. And what's going on there is that, so this looks the same, right? But then notice that there's nothing down here saying this is a temporary situation. This is a permanent thing. And so you get this alignment of these molecules. They start to line up and they start to feel the negatives and positives on each other. And they like to hold together like that. They could do it this way, end to end, or they could like line up like this so that they're crossing over side to side. And after lab, y'all are now quite familiar with how much I love Excel. So, of course, I've written a little Excel graph here to kind of demonstrate this. So what we have plotted in orange here is we have the molar mass along the x-axis. Okay, so we're increasingly heavy going to the right. And then we have their, let's see what I do, boiling points. We have their boiling points graphed along the y-axis. And so you can see, in general, as molar mass increases, it causes that to be harder and harder to boil. And that should kind of make sense, right? That if you have a denser or a heavier molecular mass, molar mass, then it's harder to give that enough kinetic energy so that it goes into, boiling means transition from liquid to gas, so it's harder to give it enough energy to get into a gas phase because it's a bigger molecule, right? So then, if we also plot down here on the bottom, the molar mass versus boiling points of this group of molecules, we see, look, this is a whole different population of molecules. And the difference is that the orange ones, ethane and propane, all these guys are non-polar molecules, right? So they only have those dispersion or London dispersion forces, right? They only have those, whereas the ones in blue here, they're polar molecules. Ethanol or propanol or propylamide, any of those, ammonia, they have a permanent dipole moment, and it causes all of their boiling points to be higher values, right? So look at this one. Let's see. What is this guy? So that is ethane. Molar mass is 30, right? And its boiling point is negative 89 C. That's pretty cold, right? But anything above negative 89 C at 1 atmosphere pressure, then ethane is going to be in the gas phase. Compared to methanol, methanol has a very similar molar mass, 32 versus 30. That's really close. But look at the massive difference. Boiling point for ethane was negative 89 C. Boiling point for methanol is 65 C. Extremely different, and that's because of the polarity of the molecule. All right, well, let's look at another system here. Now, I want to set this up a little bit, what I'm doing here. So if you look at your periodic table and look at where sulfur, selenium, and is that tellurium? I forget what TE stands for. Or if you look at antimony, arsenic, and chlorine, or iodine, bromine, phosphorus. So you look at the graphs and you can see, look at that. Let's see. The boiling points tend to go up Yeah, that makes sense, right? So if you go from H2S to H2SE, see, I'm going straight down on the periodic table, so I'm getting more molar mass. So H2S has a relatively low molar mass. H2SE, they're bonded exactly the same way, the blue ones are, but the SE is a heavier atomic center, right? So that's a higher molar mass, and so it has a higher boiling point. That makes a lot of sense, right? But now let's go the other way. TE, go up the table to Se, right? Go up the table to sulfur, and right above sulfur would be nitrogen, right? So I want you to look at this graph and predict where you think the boiling point of, I'm sorry, not it's H2O, right above sulfur is oxygen, where you expect the boiling point of H2O to be. And then let's do the same thing with these, with antimony, arsenic, phosphorus, and right above that would be nitrogen, NH3. So where would you expect, following this graph, where would you expect the boiling point to be? We can do the same with the red one. All right, so you've got your projection of where you think this should be. Then I'm going to uncover where it really is. So that's where it should be, but it isn't. The actual boiling point of water does not follow this trend down through here. Instead, it is at 100 C. The actual boiling point of HF is much higher than you would expect from this line. The actual point of ammonia is much higher than you would expect from the green line. So what's going on with this? So all of these, everything on this graph represents polar molecules. So these guys do have that dipole-dipole interaction that I was talking about. But now we're going to talk about that third one. It's a very special kind called hydrogen bonding. The reason we give it a special name all of its own is because look at how drastically different the properties involved with this chemical are. You get this massive spike in the temperature, the boiling point of H2O relative to these other dipole bonded compounds, because it has to do with sizes, but it's because oxygen, fluorine, and nitrogen work a special way, and we're going to call these hydrogen bonds. So if you think back to ionic radius, this should have been one of the periodic trends that y'all talked about in Gen Chem 1. It's about the size of the ion sphere. And hydrogen bonding only works for nitrogen, oxygen, and fluorine because those ions are so small and there's so much charge concentration on the surface of those ions that it leads to an unusually strong type of dipole interaction, and we call it hydrogen bonding. And water is a good example. So you have now, hydrogen bonding is not the covalent bond on hydrogen. There is a covalent bond linking hydrogen to the oxygen in the water molecule. That's not what we're talking about. What we're talking about is this very, very positive atomic center on the hydrogen here, seeing this very, very negative, but also small negative zone around the oxygen. And because this atomic center is seeing this negative, very small area here, it's a concentration of forces. And so you get this very strong intermolecular, call it hydrogen bonding. So it has to be hydrogen, and it has to be either oxygen, as in this case, or fluorine, or nitrogen. So now another factor that is involved here is because there's an extremely large difference in the electron negativity between hydrogen and either oxygen, fluorine, or nitrogen. So you get a very large difference in electron negativity, and then you get a very small size of the H side, and you also get a relatively small size of the F, the O, or the N side. That's what leads to the hydrogen bonding. Okay, so we're making a big deal of hydrogen bonding. And you might ask, why does it matter about this hydrogen bonding thing? Well, it turns out that it is quite important to all of you, whether you realize it or not. Right here we have a DNA double helix, and I'm sure in biology class in high school or here in college you have heard about the bonding of the DNA strand together. You get the one strand held to the other strand by the interaction between the nitrogenous bases stacked on the sugar backbone, right? These are those bases that we talk about being held together. Held together by what? I'm sure you just guessed what I'm going to say here. That, look at that, we've got, for thymine, we've got this oxygen system here, and it's looking across the gap at this H sticking off of this N here. Oh, wait a minute, what we got? We've got an oxygen and we've got H's involved. We can call this a hydrogen bond. And we talked about how strong that is, right? As intermolecular forces go. Here's another one. So we got nitrogen and a nitrogen bonded to an H. Yep, that counts as well. So you get this very strong hydrogen bond bridging across between these bases. That's what holds your DNA strands together, is hydrogen bonding. And so by looking at the intermolecular forces, we can start to predict some of the macro scale properties of fluids. So if you look at, so viscosity is a measure of the resistance to flow, right? How much it resists flow. And so if you look at something like benzene here, 6.25 times 10 to the negative 4, and don't worry about what the units are. If you have to deal with them, I'll help with that. It's newtons seconds per square meter, but that's a pretty low value as compared to, let's look down here at water. Water has a relatively high viscosity at 1 times 10 to the negative 3, and that's because of that hydrogen bonding going on in it. Now, certainly there are things here. I've referenced molasses. There are liquids that do have a higher viscosity than water that resist flow even more than water will. And we can also talk about surface tension. So that drop that I was talking about holding together as it melted off of that ice cube at the very beginning, right? The reason it forms that spherical uh, shape is because you have something called surface tension when you have an attraction between those hydrogens on one molecule of water and oxygens on the next molecule of water. Yep, that's a hydrogen bond. And they start to try to hold that liquid drop together in a spherical shape. Or if you have like a big surface of it here, we've got some sort of bug. Biologists will tell us what kind of bug this is. And it's just kind of like hanging out on the surface of water. It's exploiting the idea of a strong intermolecular force between those water molecules such that it can like sit on top of the water without apparently getting eaten by fishes. And of course, up to this point, I've only talked about the intermolecular forces between like molecules. Well, I guess for the DNA, I branched out a little bit, but between like molecules, but it doesn't have to be. You can have intermolecular forces in the sense of adhesion, like if you think about water sticking to glass, like if you rinse a tube like a glass straw out with water, you'll get some water just kind of hanging out in there, not wanting to let go. Or you can get cohesion. The contrast here is adhesion is sticking to a separate surface, whereas cohesion is resisting sticking to a separate surface because it had rather stick to the rest of the liquid. So we talk about a meniscus when we measure in a graduated cylinder. This is a typical water meniscus that warps downward. But if you were to, and I wouldn't recommend it because mercury is kind of dangerous, but if you were to measure mercury with a graduated cylinder, it actually domes upward because the intermolecular forces with mercury hold together more than they want to hold to the glass. And so you get an inversion of the system, and you would actually have a dome up meniscus, and you'd still read the maximum curvature, which in the case of cohesion would be the top of it instead of the bottom of it like we do with water. All right, well that'll end us up for now on liquids and solids and condensed phases. Now, next lecture we're going to go much more into those phase diagrams and phase transitions. So I put here 10.3 and 10.4, but really probably you should have taken a look at essentially all of chapter 10 at this point. Now, I know we've not really talked about lattice structures yet, but solid state and different phases we've talked about, and then we're gonna focus next time on these phase transitions and on phase diagrams and how to read those.